So as you see, the title is the title of the paper roughly. That paper, as you know, has been submitted to Journal of Fluid Mechanics, and it is now in the revision phase. But the referee reports are almost glorious. So I'm sure that it will be accepted. The story, at the beginning, there is some history which goes back to Leonardo da Vinci, whose picture with turbulence is shown here. But let me go to the next. So I have to, that's it. Yeah. The first slide is Leonardo, and it's Codice Atlantico. Codice, that's the Italian for the Latin codex, a document, big document. Okay. Now, here there is an interesting story. Leonardo died in 1505, but it was born significantly before, and during his entire grown-up life, he collected sheets of papers on both sides, and they were not bound; they were loose. And after the death of Leonardo, many years after the death of Leonardo, because he was died in 1519 or so. So there is a sculptor, Pompeo Leoni, who got hold of many documents of Leonardo. He organized them with criterion of his own. The result was called by him Codice Atlantico. Rather close to the beginning of the Codice, there is a text without picture. It is about the decay of turbulence, the main subject of our paper. But because that is discussed a long time ago in my book, which was published in 1995. It's a long time ago. That's nearly 30 years. And and then there's, when you look at the Codice Atlantico as edicted by Pompeo Leoni, and you try to guess when did Leonardo write his things about the decay of turbulence, you come up with something 1480, which could be the beginning of his stay in Milano. He was born near Venice, not Venice, Florence, yeah, Florence, sorry. Yeah, Florence. Near Florence, and then moved to Milano for a long time, and then back to Florence, etc. Was it really 1480 that Leonardo was interested in hydrodynamics? It took a very long time find that this was wrong. If we go to the last, the third column, the accurate dating of Codice Atlantica was discovered. I mean, this is horrible because, oh, didn't tell me that this is a horrible thing.
The problem.
Look.
C'est mieux ou pas?
Hein?
C'est mieux?
Bah non.
On peut pas faire autrement.
Ça va?
Là, on voit bien. Regarde.
No, can't read it.
Mais si, regarde.
Here. It's getting better. Move it up.
On peut la mettre.
Yeah, that's it.
C'est bon?
Yeah, that's it. Okay. Now, this is of course not my computer, because there are, in order to be able to zoom to Kyoto and back and so on, there are constraints. So we have to use another computer. So there is a contemporary, Augusto Marinoni, an Italian who works in Milano, and he died recently, 1997, long after Leonardo. He was a philologist from Milan, one of the greatest specialists of Leonardo da Vinci. For this, he used his deep understanding of the various phases of Leonardo's activity and also the evolution of his handwriting. According to Marinoni's late 1990 work, published posthumously in 2017, a few years after the death of Marinoni, the text of Leonardo about the decay of turbulence is dated around 1505 and not 1480, 25 years later. Now, the text of Leonardo about the decay of turbulence is about 25 years later. It is interesting to note that a year before that, in 1504, Leonardo was very busy planning to divert the course of the Arno River from Florence in order to deprive Pisa from water. Leonardo never tried to hide his interest in practical problems, occasionally war, and particularly Italian cities frequently were at war. But the paradox, it turns out that more than 5 centuries later, the law of decay, turbulence, is still an open problem. As we shall see, we have made some important progress, but the problem is not solved yet. So that's one of the few classical things which is really tough, although it does not require neither general relativity nor quantum mechanics. So let me move to the other thing. No? Yeah. Okay. Now we go into the further history. Between 1505, roughly, And almost now, not much happened. But around 1938, there was Kármán, von Kármán. Actually, his name sometimes is published as de Kármán, in other words, as von Kármán. This one was published as a de Kármán in a British journal. And so Kármán established that the mean energy of turbulence should decrease very slowly. This is precisely what Leonardo said, very slowly. Why? Because the functional spaces were not known around 1500, so slowly. Could be a power law or something, who knows? Not yet invented. Then Kármán established that the mean energy of turbulence should decay very slowly, indeed like an inverse power of the time elapsed from the initial time. 3 years later, Kolmogorov, by the way, our next speaker is the grandson of Kolmogorov in the scientific sense. So Kolmogorov found an algebraic mistake in Kármán's calculation. Kolmogorov himself found another inverse power, t to the minus 10 over 7 of the time elapsed. This likewise was wrong, because he was assuming a certain invariance properties of Loyansky, that's a Russian thinker, contemporary of Kolmogorov. But that was proved wrong by Proudman is a Brit and Reid is an American. Did his postdoc with Proudman in Cambridge. Now, Proudman and Reid proved that the constancy of the Loyansky invariant is wrong by using a closure for the statistical theory of turbulence known as the quasi-normal approximation, QNA. In this method, the fourth order correlation function of the velocity is expressed in terms of the second order correlation function, pretending that the solution is Gaussian. 9 years after the Proudman-Reid paper, a Japanese guy, Ogura, published a paper demonstrating the QNA can predict a negative energy in some band of wave numbers. What is that? This was violating the probabilistic realizability of QNA. So people discarded this. However, actually the proof of Proudman and Reid seems to be correct. A key remark is that the small wave number dynamics is dominated by what we can call beating interactions between two wave vectors nearly opposite and moving in opposite direction. Yeah. The negative energy range obtained by Okura is at much higher wave numbers and does not contribute to the behavior of the Loyansky integral at small wave numbers. So, so they were right. The Loyansky thing is not relevant, although the proof were purely within QNA, but QNA is wrong at some places and reasonably correct at others. Okay. it is this one? That's it, yeah. So we go to this one. The Burger's equation as a model of the energy decay of turbulence. Now, this originally was done already with Khanin, Pandit, and Dipankar. All three are there. So here, of course, I'm reminding you what the Burger's equation is. That's been around for a long time. There's no need to read it to you. It is a kind of a poor guy analog of the Navier-Stokes equation, yes. The initial velocity is denoted E0, and it depends on the Lagrangian coordinate A. It is often convenient to work with the potential related to the velocity by U is, of course, minus grad of the potential. The Burger's equation can be backed into the heat equation by a nonlinear transformation introduced by Hopf-Kohl. One consequence strongly emphasized by Burgers in his 1974 monograph is that the zero viscosity limit of the potential has a very simple expression represented in terms of the initial potential, namely the potential in Eulerian coordinates. Phi at point x at time t is the maximum of the initial condition of the initial potential minus a parabolic term. That is an extremely important result, which has no analog for Navier-Stokes. So that helps a lot with the Burger's equation. However, many people, when they found that Hopf-Kohl had actually solved the Burger's equation, thought that the Burger's equation would be trivial and certainly not a good model for Navier-Stokes. It took a long time until people realized that the Burger's equation is highly non-trivial. I can tell you that I was invited at the 100th birthday of Burgers. He was dead at that time in Holland, and I spoke to his children. They had spoken to what they thought was a great man in fluid mechanics in the 70s or 80s. And they told him that the Burger's equation, after the solution of Hopf-Kohl, it appeared that the Burger's equation was necessarily trivial and not a good model for Navier-Stokes. That was completely wrong. So one of the very useful thing of the Burger's equation is has this max representation. By the way, there is a controversy whether it is Hopf-Kohl who found it or Burgers. My own recommendation is the following. If you read the papers of Hopf-Kohl many times, you don't find this thing here. Burgers has it in his book and claims that it was essentially obtained by Hopf-Kohl, because Burgers was an extremely modest person. I think it was Burgers who found it. We shall see. So now this is a very important formula, and it has all kinds of consequences. Let me skip this. It's not essential. Okay, here. That's it. Yeah. There is a lot of work that is concerned with the Burgers equation, where the potential initially is Brownian motion in space. But that has been extended to what is called fractional Brownian, which is a variant which is Gaussian also, but is not a Markov process. Now, not being a Markov process, that means there is a lot of memory. It's very painful. For example, with Sinai, Uriel, and Scher, we proved results for the Burgers equation with Brownian initial condition in the potential. And then Molchan tried to extend them to fractionally Brownian motion, which is not a Markov. It took him 15 years, and he succeeded. It is not surprising that one of the referees of our paper was Molchan. So what is happening is that one can construct geometrically the solutions with Brownian initial data, with fractional Brownian motion, and then one can show easily that in the Eulerian velocity completely loses the Brownian thing, apparently. The initial data for the potential is and the velocity is infinite. It's a distribution. But immediately for any positive time, whoop, it goes into this thing, namely hop, 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 hop. And proving such things is not trivial, and you will see. So here is the first thing that was not published yet. Self-similar evolution of the potential with fractional Brownian motion. Now we assume that the initial potential has this thing, and that it is easy to show that what it means is that when you boost the Lagrange by a factor lambda, positive lambda, then with Brownian, it will be lambda to the 1/2, the famous 1/2 of the Brownian motion that everybody knows. When you want to find how much noise there is in an opinion poll and things like that. And now it's lambda to the h. It's between 0 and 1. And then one can easily show that the Mech's formula is modified by this factor lambda into what is here. Do you see the cursor here? Yeah, you do.
Yes.
Okay. And oops, oh, sorry. Yeah. And it is also rather easy to look at the two factors, lambda to the h and lambda square and so on. And you can scale things out and then prove rigorously that when you do a factor lambda to the to the Illyrian position, then what you can get out of it is a lambda squared over the time and so on. Now, a consequence of this is that when you square the velocity for the velocity, you have to take the gradient of phi and square it, etc. But it is rather obvious, and you find that the energy varies like a power law t to this 2h minus h over 2 minus h. However, there is a possible bug in here, because at time t equals 0, velocity is a distribution and not a function. It's infinite everywhere. So infinite energy initially. And proving that for any positive time, the energy is finite is not trivial. This was done a few months ago by this guy. And that is absolutely necessary in order to prove that the energy decreases like a power law. So power law, that's very closely related to what one calls self-similar dependence. And however, the proof, mathematically speaking, requires the proof that the energy is finite for positive t. And now that's a kind of boring result, because there are power laws in the initial data, there are power laws later, etc. Isn't all this boring? If you want Burger's turbulence to be anywhere close to Navier-Stokes turbulence, the least you can require is there should be a lot of fractals, more precisely multifractals, a concept that was introduced by Giorgio Parisi and myself a long time ago. But the multifractality on which we were working based on experimental work was small-scale multifractality. And Burgers hates that because there are shocks and shocks and shocks. There's no way for multifractality. So the new idea, large-scale multifractality. And that was the central result there. Just a moment here. That's it. Yeah.
seems to have gone back.
That's it. Yeah. I'm coming there. No, because it's very different from my computers. It's the opposite of what I used to. So infrared, large scale, infrared in the jargon means large scales. Multifractality for burgers. Now this was conjectured, just a conjecture, for the first time in Rome on October 3rd, 2022. But the proof took a long time, well, several years. And the first idea, which was not be interesting but didn't quite survive, was to say it's not enough to have a single Brownian thing with an exponent h. They're called the Hurst exponent. You have to have the exponent varies in the initial condition. There is a place where you take an h1 and an h2 and an h3 and so on, like in this picture there. And let's coming to the conclusion here. That's good. In the discussion about multifractality, one must underline that the best wind tunnel data are inconsistent with a single fractal dimension characterizing the energy cascade to small scale. The data require a multiplicity of fractal sets. The Parisi-Frisch model invokes global properties of the 3D Euler equation, such as infinite number of scaling groups, but is not deduced from the basic equation. Indeed, the mathematics of the singularity for the Burgers equation is still in its infancy. Haha. For other problems of nonlinear dynamics, multifractality is a common phenomenon which can be deduced from the basic equation. A number of examples are known. Attractor of dynamical systems, Benzi-Paladin, Parisi, Ulpiani, and so on. Singularities of functions in Sobolev and spaces, Jafar, and so on. Is there a technique to prove a multifractality theorem for Navier-Stokes? The standard ersatz for this equation is, of course, the Burgers equation. With smooth initial data, the Burgers equation will develop shocks which are trivial monofractal structure. When the initial velocity is a Brownian motion, non-trivial fractal small-scale behavior appears, but multifractality is very much in doubt. When the initial potential is Brownian, there are no accumulation of shocks and small-scale fractality is ruled out. A more promising way to get multifractality from the Burgers equation is to consider a large-scale Brownian initial potential with a Hurst exponent which is piecewise constant, as in the previous slide, or simply discontinuous, as is the solution studied by our next speaker, Khánin. Proving this rigorously seemed to me in late 2022 could take many years. I was wrong. It took Kostya barely a little more than 1 year for the first proof to, not published, but to disseminate it to our favorite friends who are all in this room. Yeah. During this time, another person who is in this room, Dipankar, was able to check numerically the multifractality, first speaker of this afternoon. The current state is that the law of temporal decay of the energy for Burgers and perhaps Navier-Stokes is not a pure power law, as was assumed by Kármán and Kolmogorov. Such multifractal investigation have been carried out by a mixture of Canadian, French, Indian, and Japanese turbulence addicts. That's it. Any question?
So, I mean, is the multifractality assumed at the level of initial conditions?
No. Multifractality is not assumed, it's derived.
Derived from what?
From the Hurst things, random Hurst things in various intervals, and they have to be large.
Kostya's talk will cover that.
He is entirely Kostya's talk will be entirely on this. So there's no need to ask this question now.
Now, the
But
question is the question is what's the hypothesis of initial conditions in order to obtain the non. I mean,
that will be, you will speak about it. Yeah, this is, yeah. So, any other question? Okay, then maybe Julien can switch the thing.
Okay, can you hear me? Right, thank you very much for. Okay, Uriel asked me to speak up. Okay, so thank you very much for joining us on this celebration day. Well, it was celebration yesterday, but in Russia it's celebration today, and many people are, and many people, and the Pope, yes, and many people are celebrating it entirely for the whole 4 days, I guess. Anyway, let me just, so the purpose of my talk, I want to describe particular random potential which results in multifractal behavior for the solution, large scale multifractal behavior of solution. So I will start with basics, which was already said by Uriel. So Burger's equation, inviscid Burger equation is written here. Like you can see it, but anyway. And then there is a initial value problem we are considering. So Cauchy problem, we start with initial data, giving the initial potential. So velocity is a minus gradient of initial potential. And then potential at any time t is given by Mach's formula, where A is Lagrange.
Yeah. If you turn to the, we don't hear if you look at the screen. It's you can look here or on your screen.
Well, yeah, when.
Your head to us.
All right. So it's initial value problem, and that's formula, Mach's formula, which gives you solution, the potential of the solution at time t, which is the maximum over the initial coordinate A, Lagrangian coordinate. So Mach's formula involves the initial potential phi sub 0 A minus the quadratic term, parabola term. So this is all well known, and I also will be using a bar, which is the argmax. So this particular value of A.
Is arguments.
Yeah, which is argmax. It's a particular value where max is attained, right? It's denoted by a bar, which is of course function of x and t. So for giving x and t, there is a point where things originated, which brings its maximum to this expression. And so, as I said, and Uriel said that we're going to consider initial condition, initial potential, which is a random. So realization of a certain random process. And this random process is supposed to be translation invariant. not in terms of phi, but in terms of the velocity. So it means that the increments or derivatives, special derivatives of the potential, supposed to be translation invariant, right? So the initial velocity field is translation invariant, which is natural assumption. And so what we are going to look at is what is large scale, what we call large scale multifractality, which is the following object. So you look at the velocity at time t at particular point, and this point doesn't matter. It can be any point because of translation invariance. So in particular, you can use the origin as a reference point. You take absolute value, so you take speed, absolute value of velocity, and take it in power m, which is any positive number, or any number, not necessarily even positive, and then you average it with respect of a initial random potential. And then what we want to show that this averaging, this kind of structure function, behaves like time and certain power. Of course, it will be decaying with time. It's decaying turbulence. So this power will be negative, S on m, but will depend on the moment. M is a parameter, which moment of the speed we want to consider. So S will be function of m. And so absence of multifractality, it means that that S on m is a linear function of m. So there is one scale, and that will be not multifractality, not fractality at all. Then we will have, sometimes we'll see bifractality, and this means that Sm consists of two linear pieces. And that's quite common in Burgers equation, that you can have bifractality. Usually it's for many quantities, not only large scale multifractality, but small scale as well. So if you consider true structure functions, which is velocity difference in small distances, they will be behaving bifractally because of shocks, and that's well understood. And then, so this is bifractality, but we're more interested maybe in true multifractality, where Sm is generally nonlinear function. It's not consistent of two linear pieces, but it has some nonlinear behavior, which is in non-trivial way depends on the power, on the exponent m.
What is the difference between multifractality and true?
Well, I'm saying true multifractality means that S on m. So I would say, so if you have function which consists of two linear pieces, it's non-linear function. But if you want to have function really kind of smooth non-linear function, that I would call true multifractality. Right?
So sorry, you're interested in the multifractality in time, in space.
So
It's
okay,
not the
so
turbulence we are generally interested in space.
okay, so the behavior in large time is coming from the large space behavior, because the Legendre coordinate, Lagrangian coordinate at initial time corresponding to point x at time t will be far away. So it's coming from a kind of large space behavior, but large time as well. So of course we are considering behavior at large times, which is asymptotic behavior, but we also, but effect which we will observe comes from a large scale behavior of initial potential in x. So everything, all randomness coming from initial potential, and the initial potential, it's behavior at a large scales what governs what effects we want to consider. Anyway, let's see what we have. And so first, so the potential which we'll be using, we call it oblivious fractional Brownian motion. So let me step by step introduce what we're having here. So first, what is a fractional Brownian motion? I denoted WH on x. So it's a process sometimes in time, but here it's in space. X is a space variable. H is what is called, has many names. It's Hurst exponent or Hurst index or Hurst parameter. Different textbooks use different names. So I mostly would say maybe Hurst exponent. It's parameter between 0 and 1. Now, if you open the Wikipedia page for fractional Brownian motion, and Wikipedia is not a bad source, that they will give this formula for the correlation function of this process at point x and y. And formula doesn't tell you much. I mean, first of all, it looks ugly having these absolute values everywhere. and it's just not very good formula, I think, although it's correct. And so then I would introduce how you should think about fractional Brownian motion, and then I would move to oblivious fractional Brownian motion. Right? So Gaussian process, it's a Gaussian process, first of all. And Gaussian processes are completely determined by their correlation function. And correlation function is presented here. You have to check that it's positively definite, but it is when h is between 0 and 1. But what really happens here is that you want to have process which start at 0 at the origin as a normal Brownian motion. The value of this process at the origin is 0. And then you look at the second moment. So the first moment of W is 0. And you look at the variance, the second moment of it. And you want it to behave like x in power 2h. So when h is equal to 1/2, this is normal diffusive behavior. So this variance is proportional to the distance. But here you want it to be either subdiffusive or superdiffusive, depending on whether h is greater than 1/2 or later than 1/2, smaller than 1/2. But remember that h is between 0 and 1. You cannot go beyond 1. It doesn't make any sense. All right. Now, I just want to point out here, this simple calculation shows that if you want to require that second moment behave this way, which is a natural way natural desire to have, then correlation function indeed will be what is giving formula above. It's uniquely determined, this assumption of W square behaving absolute value x in power 2h, uniquely determined correlation function. And that's a little calculation here, that if you take difference of 2 points, square it, which will be increment. You also assume, of course, that increments are stationary. You want to have process with stationary increments. So increment between x and y is the same between 0 and y minus x. So that is the second moment for this increment. And if you write it down, then you will get formula for formula above. Now this is already better. It's just Gaussian process with stationary increments, translation variant increments, and with the prescribed behavior of the second moment. Now, this process is known to be self-similar. So in distribution, if you scale by factor a, 8 here is just, unfortunately, it's not Lagrangian coordinate, just a number. Sorry for using it in two different sense. So if you scale x by some number, then this number appears in power h in front of w h on x. And this is understood in distribution sense. So rescaling would have the same distribution up to a constant factor. And the regularity of this process it's a little bit less regular than so it's a Hölder exponent h basically here. If you compare the values at two nearby points, y and x should be very near to each other, then asymptotically behave like y minus x in power h, almost h. It's like in Brownian motion. It's not square root of distance, but it's slightly less than square root of distance, or maybe logarithmic factor or something. But basically it's square root. And here it's given by factor h. Then what I want to say next is a much better understanding, representation of the fractional Brownian motion, because the previous formula doesn't, so of course process will not be Markovian when h is not equal to 1/2, but doesn't tell you how to deal with it. If you just know it's not Markovian, it's very difficult to deal with it. You need certain independence. And so the formula which is written above is an integral representation, not of a fractional Brownian motion yet, but the object very, very closely related. It is W wave on h, and this is just integral of a function t minus s in power h minus 1/2 dws. And ws is just white noise, normal white noise. So w is just normal Brownian motion, d of it is just white noise. So it's a stochastic integral, but the simplest possible stochastic integral, because what you integrate is non-random function. It's just deterministic function which you integrate over the white noise. So in this particular case, for example, you should not ask what kind of stochastic integral Ito, Stratanovich I have. It's the same thing. Just it doesn't matter. It's a very simple object. And the thing is basically fractional Brownian motion. The only thing is that the integration started from 0. So you start from Zero is the initial condition, and the formula will not have explicitly stationary increments. So it's not true that increments in different places are exactly the same, have the same distribution, just because you started from zero. So what you need to do, you need to run it for a long time, and then after this long time, you will get stationarity. So it's asymptotically stationary if you increase your time and look at this, not starting from zero. So you use this formula and then run it until a long time t, and suppose you start at that point where you run it. And then what you see after that will be increasingly stationary increments in the limit, exactly stationary in the limit when t goes to infinity. So this was realized by Mandelbrot and Van Ness in 1968, 15 years later than Paul Levy introduced his formula. And then what I said, I run it from zero for a long time, and then say, okay, let's start at minus infinity, and run it from minus infinity until time t. And that's exactly what they have written. So you have integral from minus infinity to t, minus integral from minus infinity to zero. So this is increment from minus infinity to zero, you achieve this long history. And by that, this formula also already have, it's basically the same formula, but in the limit of starting phi in the past. And it has a factor ch, which is 1 over gamma function of h plus 1/2. That is just a normalization factor. Forget about it. It's just a constant to make it formula for the correlation function or for the variance exactly what we wanted. Otherwise, it would be proportional to some constant. It doesn't matter. It looks a bit mysterious how gamma function appear here, but you should not be too concerned about it. It's just a number. And this number depends on h. And so just for those who don't remember exactly gamma function is given by definition of gamma function at x, and x is just integral written here, t in power x minus 1 e to the minus t, and it's known that in integer points it's equal to factorial of a previous number. So at 1 it's equal to 1, at 2 is also equal to 1, at 3 is equal to 2, and so on. And it's also known in some half integer numbers, because gamma at 1/2 is equal to square root of pi. And that's some numerology, which is not essential for us. Anyway, so that's a better representation of the integral representation of fractional Brownian motion. I give another representation of fractional Brownian motion, which is random walk approach. This is very recent. This was done by the Alan Hammond and Scott Sheffield in 2013, two probabilists. Alan Hammond is in Berkeley and Sheffield in MIT now. At the time they were not. And so this what I described below is a very nice, I think, approach how to construct random walk, not simple random walk, but just random walk going to nearest neighbors, one-dimensional random walk, which in a limit, after you scale it, converges to fractional Brownian motion with exponent h. But h here in this approach should be between 1/2 and 1. We are not going from 0 to 1/2. Now, the difference between h less than 1/2 and greater than 1/2 is that when it's greater than 1/2, it is positively correlated. So basically, you want, to a certain extent, to mimic in the future what you prefer to do in the past. And when it is h is less than 1/2, it's negatively correlated. You don't want to mimic. You want to be original. You want to kind of have your own character. And so the approach which I describe here, valid only for positively correlated. The authors are asking whether you can extend it to negatively correlated, but probably not. Nobody was able to do it. So maybe it's either impossible or you need another idea. Okay, so idea is the following. You want to mimic what you did in the past. So basically you come to a point n and you want to decide whether you go to the right or to the left. And you do the following. You sample some point in the past with certain probability distribution, which I'll describe later. And then you see what you did in the past. If this point in the past which you sample, after that you went to the right, then you go to the right. If at that point which you sample, you went to the left, then you go to the left. And that's what is the basic idea, what you want to do. Now the probability distribution, so let's consider the case when we choose this. So we, at time n, we want to look at n minus k in the past. So we go k steps in the past, and probability distribution for k will be decaying like power law. 1 over k in power 1 plus alpha. Alpha is positive. So this is a summable thing. So that's what I want to use. This probabilistic law with subparameter alpha. Alpha will be related to h in the moment. Is it clear what I'm doing? Okay, fine. Now, how you do it rigorously? Because you don't start at 0, and you want to construct the whole. So you do the following thing. You consider all integer types from minus infinity to plus infinity. 0, 1, minus 1, all times. And for every time, you sample n minus k according to the law I said. So for every point, you do this arc, a red arc. And arrow show that this is parent of a point here, right? So n and the parent n minus k. And that is for every n. So you get collection of these arcs. And then, of course, if you went to this point, and then from this point, maybe parent was another one, that behavior will be the same for all 3 points. So the question is like everything split on clusters connected by this arc. And the question is how many clusters you're going to have. And turns out there's this dichotomy. You either have one cluster or you have infinitely many clusters. And this was proved by, it's not very difficult, but it was proved by Scott Sheffield and Alan Hammond. And so if alpha is between 0 and 1/2, then almost surely you're going to have infinitely many clusters, which are not connected between themselves. And if alpha is greater than 1/2, then almost surely there exists only one component, one cluster, right? So one cluster is not very important, not very interesting, because all of them are going in one direction. So it's basically ballistic movement. But when you have infinitely many clusters, that is a promising thing. And so in order to generate random walk, which will be scaled to fractional Brownian motion, you do the following. You take some alpha less than 1/2, and you see that formula will be h is equal to alpha plus 1/2. So alpha is h minus 1/2. So between when h is between 1/2 and 1, alpha will be between 0 and 1/2. And then so you first sample all these arcs. So you sample clusters. And then for each particular cluster, you choose +1 or -1. So if you choose +1, you will go to the right. If you choose -1, you go to the left, independently. And now you completely determine your random walk because you start at the origin and you see what is the cluster at the origin. So you go to the right, then you see which cluster is new point. You go to the right or to the left. So you just follow this pattern. This random walk completely determined by the random cluster you created and by the choice of +/-1s. And now if you take this particular random walk, you're going to nearest neighbors, then rescale it, then the process, I rescale it by n to the -1/2 of minus alpha, and I take random walk at point nt, then it converges when t goes when n goes to infinity, it converges to wht, to the fractional Brownian motion with exponent h. So like normal random walk scales to the Brownian motion, this one scales to the fractional Brownian. And I think this is a very good description because it gives you some kind of idea. It also can be used for numerical calculations, right? Because it's easy to sample thing and then. All right. So that is fractional Brownian motion, which does not produce multifractality. And now we are going back to what I started this slide. This is a oblivious fractional Brownian motion. So oblivious means the following, that fractional Brownian motion is Markov process, a non-Markovian process. So it has memory. But we want to consider the following situation, that there are certain intervals on the real line at time 0, which is a real line of Lagrangian coordinate A, and it's split on certain intervals. And on each interval, you use fractional Brownian motion. but these pieces are basically independent. So one branch fracture branch is here, another here, and so on. And so basically it remembers within interval, but then with certain hit of the head, your memory loss, and you don't remember what was in the past anymore, and you start from scratch. Now, literally speaking, the process which we want to construct will be continuous process. So it does remember a little bit of what was in the past, because otherwise it will be discontinuous, but the increments will be independent. Increments of this process within different intervals are independent from each other. And that's obvious. We actually believe that this process must be of interest for financial math as well, because actually what Mandelbrot and Ness were doing had some financial math implications, and people in financial math, they use fractional Brownian motions to model the share prices and so on, because it's natural to expect that you have memory of what's going on. I mean, it's natural to assume that it's independent, increases and decreases of share prices. But at certain moments, which are kind of financial crisis, after this, maybe you start from scratch. You don't remember what was in the past. So it may be of some, but we checked with people doing financial maths, and this object was not considered in financial math. Oblivious fraction Brownian. Okay, so what we want still keep translation invariance of the process. So we want to have point field, and this point field, which is described by this little black marks on a real line. This real line is a line of parameter A. It's split on an intervals of certain length, and we want this splitting be translation invariant. And so the first question, how to do this splitting? So we want intervals to have random lengths. So we want to have certain distribution of the length of interval. And this length will be proportional to L in power minus gamma. Gamma is a parameter greater than 1, so that integral is finite. So basically you want to choose independent lengths all the time, and that would be your intervals. But again, you have to start from somewhere. Like in the case of Levy and Mandelbrot for Ness, you should not start from zero. So you should start probably in minus infinity, or say minus n, and then keep adding intervals of independent lengths. And then by the time of reaching the origin, you achieve translation invariance in the limit when you started to minus infinity. And this can be done, but then you have to set a restriction on gamma. So gamma cannot be just greater than 1, it should be greater than 2. And let me explain it to you. So basically, if you want to sample the thing, so it turns out that you have independent intervals of independent lengths. And then you want to say, what would be probability distribution of interval covering particular points, a point origin? And you can easily understand that if interval is long, it's more chances that it is will cover the origin. I mean that probability distribution of interval covering particular point you are interested in, fixed point, will not be given by this L to the minus gamma, but in fact it will be given by L to the minus gamma, L times L minus gamma. So if you get extra factor L because of this fact that long intervals have more chance of covering point than shorter intervals. So it will be more clear for the next slide. So how you can realize this process? Yes, you can write it. You can take process I described starting with time at point A equal to minus n and take limit when minus n goes to infinity. Or you can do the following. You first sample L naught, which is interval containing the origin. The length of interval containing the origin. I said origin is just reference point. So this will be probability distribution 1 over L naught divided by gamma minus 1. It's extra factor L on top, right? So that would be your L naught times P L naught with the probability distribution of interval. You sample this interval. Then you want to sample position of the origin inside this interval. That's uniformly distributed. You just choose epsilon, which is uniformly between 0 and L naught, and your interval will be minus L epsilon L naught minus epsilon. So that is fix your reference. That's interval containing the origin, and then you start adding independent intervals with independent lengths given by the factor 1 over L in power gamma. And that is how this translation variant process of process of intervals can be constructed. And it's easy to see that it is translation variant stationary process. Now, this is just the length of intervals. This is a point process. Now you sample each of these intervals. You sample independent fractional Brownian motion with exponent h. Now, in the first interval, you will sample it so that the value of the origin is 0, and that you have fractional Brownian motion until the end of this interval. On the next interval, maybe I'll go up. So you first sample, say, this interval, this red curve on the first interval. Then on the next interval, you start maybe at that point, so 0 will be here. But you get a piece of independent fractional Brownian motion, and then you raise it up to match at the end point of this interval. And then you take next interval, you get and match move vertically to match the next point, and so on. And the same you do in minus time. And by doing that, you will construct a random process, which would have, which started the origin, say 0 is at the origin, and which is continuous. You want to have continuous potential, and which has independent increments within different intervals. But this will be translation variant process. So that will be object we want to study. We want to use it as initial potential for the Burgers equation. So it was a question, what will be the initial potential? That will be initial potential. So it will be potential, you first have translation variant splitting on intervals with a power law decay of their lengths. And then you sample fractional Brownian motions, independent fractional Brownian motion. At this setting, they all have the same age. And then you have pieces, and then you match them at the endpoints, and then you get your point. So there are two parameters, gamma and h, which characterizes the resulting process. Gamma is a power law of decay of the length of intervals. H is the Hurst exponent of the corresponding.
That's what is called oblivious.
That is particularization of oblivious. Yeah, it's oblivious. So you can consider different probability distribution on intervals. But we choose one which is with power law decay. You can consider exponential decay, but it will be not working for us. So
This is the same as a forgetful.
Forgetful. Oblivious means forgetful.
In Latin.
All right.
Somehow the H will be always fixed by the, you just look at the initial condition, just impose the H in it, right?
Yeah, H is imposed in the initial condition. Like when you consider Brownian motion.
So the idea is that when you look at the increment, if it's small enough, it will always be in one interval, right? But what happens if gamma gets high? I mean,
So gamma is fixed. Gamma is fixed and H is fixed. There are two fixed parameters. For example, if H is equal to 1/2, then doesn't matter what gamma is, you just get Brownian motion. Just normal Brownian motion. Because the memory is no memory here at all, so this will be just a Brownian motion. For any distribution of intervals. But if it's H is not equal to 1/2, then you get something which is different from fractional Brownian motion. Okay, so let's see our.
H is the first exponent of the potential or of the velocity?
Of the potential.
Of the potential.
But it's the same.
It's the potential which is Brownian motion.
Exactly. Yeah. Yeah.
It's
No.
not exactly the case that was considered.
It's not integral of Brownian. So you see, there are two settings. Uriel together, Sinai, Uriel, and Eric, and so were considering integral. Yeah. They were considering a situation when you have the potential of the integral of Wiener process. And then you have complicated structure of shocks, and this fractal structure of shocks, and so on. Then George Movchan was considering the same thing when you take integral of fractional Brownian motion. But this is much more regular thing than Brownian motion, when you integrate your age, increase regularity.
Also, if I want to understand it in a more intuitive way, if I take larger and larger gamma, somehow I taking initial condition will be more and more irregular.
More and more regular.
Irregular. For larger and larger gamma. It's kind of
Yeah.
discontinuous, but kind of correlated.
Well, gamma will be fixed. I mean, it's we're not taking larger and larger value. It's just I don't know. Yeah. So I mean, if you take very short intervals, then it will be much. I would put it the following way: that you know, inside these intervals, the regularity of potential is given by H. But when you go outside, then you get certain diffusive behavior because pieces are independent. So it's a mixture of diffusive behavior because of independent pieces and fractional behaviors H inside intervals is giving H. That's what they're saying. But anyway, I want to say that this complicated structure of shocks appearing because of integration of these processes. Now Avellaneda and we're considering case when it's just Brownian motion. And then what you see at any finite time, you just see point field of shocks, and they're separated. They are not accumulating anywhere. And the same, although it was not proving, I'm sure it can be proven. It will be for any fractional Brownian motion that you will have certain point field of shocks which are separated from each other at any finite time. And this will be scaling invariant point field. And of course, the size of shocks will be getting smaller and smaller when time increases, but it will be simpler behavior.
My point was simply that the velocity is some kind of, let's call it fractional white noise. For H.
Yeah, it is derivative. Velocity is derivative of the, yeah, it's fractional white noise, exactly. Yeah, you're absolutely correct. Velocity is fractional white noise. And this notion exists. It's called fractional white noise. All right. So I'm going further. Okay. So we are interested in velocity at large time t at the point at the origin. Origin again, reference point, just any point. And we want to average it with respect to potential. So the trajectory of the characteristics, because we don't have force, is a straight line going from the origin to point A, which depends on the point on t. It is a L on t will be the point where maximum corresponding to max where max attained. It would better to write A bar. And where is it asymptotic behavior? So asymptotic behavior, well, t is determined by the following relation. That basically when you go to L on t, you're paying price in terms of the quadratic term. And this price is written here, t times L on t over t squared. So this is parabola. Forget about 1/2 because it's up to the order of magnitude formula. And that's what you're losing. And what you're gaining is maybe you get very good large value of W at this point, WLT. W is our potential. It will be oblivious already. So I don't indicate H because otherwise indices are too heavy. So you want the either you didn't go far enough, then you don't get enough advantage, or you go very far away, then the kinetic term will just kill you. So you have to have balance between the terms. That's the relation which is determined how far you go. So that the scale of your potential at that point should be of the same order as the kinetic term you're losing. And so we want to understand how this L and T behave in order to match this criteria. And basically, there are two different scenarios which you can have here. So one scenario is that just the first interval which contains this point is very long. And so long that the point, Lagrangian point, which corresponds to max, will be within this interval delta naught. And so the statistic will be determined by the one fractional Brownian motion within this interval delta naught. And another scenario is delta naught is not particularly long, maybe delta 1 is long, but it's the same as delta naught long. So not all of them are kind of order 1 intervals, they're not very long. And only after you do n of them, you reach the point A, where max is achieved. And so then then the L on T will be of the order of sum of the lengths of interval delta I until you reach this N. And so it is if LT is greater, if LT is less than 0, it's starting anyway, it's the same thing. You start from some negative n until 0, or you start from 0 until n, depending on the right or left, doesn't matter. And the first scenario, probability, of course, the probability of such event that delta is very long tends to 0. But when you average, it can give you major contribution to the momentum, right? And it's obvious that it will give you a good contribution for momentum for large enough R. So in the second case, when intervals are order 1, so how big is the potential of the point? It's order of the, you need to find variance, and square root of variance will give you order of the, can be positive or negative, but what you can attain will be of the order of the variance of the potential of this point. And so variance will be, in second scenario, will be sum of the lengths in power 2h. That is the variance inside the particular realization of the fractional Brownian motion. And then you have n of them, and they are independent. So it's sum of independent, so you get variances summable there. So that will be a relation in the second scenario. Now I notice that n and L are of the same order, simply because I said that gamma is greater than 2, and because gamma is greater than 2, the average length of interval is finite. And since the average length of interval is finite, then the total length is proportional to number of intervals, n times average value, law of large numbers. And so then you do easy calculation, and now you need to estimate. You take sum of this L in power 2h. Now L's are random variables with a particular distribution, and so it's easy to understand that the probability distribution for the L in power 2h will be giving by 1 over. So I'm saying maybe I would say the following, that so the PDF of the length in power 2h is proportional to 1 over L in power 1 plus tau. It's simple calculation. And tau is given with gamma minus 1 divided by 2h. And so you have sums of random variables, positive random variables, where decay is 1 over L in power 1 plus tau, decay of the probability distribution. And then you understand what will be the order of the sum of this random variables. So you take sum of n random variables, or they are all positive, and they have power law decay of their probability distribution. And this is well-studied object of probability theory because it's sum of independent random variables. That's not a big deal. So what will happen when tau is large? Then there is the average value of this L in power 2h, and then the sum will be order n. It's n times average value. But if average value is infinite, then it's easy to show. Well, you need certain calculation that the sum will be n to the power 1 over tau. If tau is less than 1. And it will be n log n when tau is equal to 1. As usual, when it's on the border of summable, that's a bit different. I'm interested in the uppercase and lowercase, right? And so, so if tau is greater than 1, then our relation would say that t divided times lt over t square should be square root of the variance, and this is square root of n. And this is and n is the same order as L, so it's square root of L and T, and it gives you that L and T will be order T to the 2/3. Whenever you have the second scenario, it's as if you are just having Brownian potential, and L will be order T to the 2/3, and the velocity will be order T to the minus 1/3 divided by T, And if you take in power m, it will be t to the minus m over 3. And if tau is less than 1, then it will be the same thing, but instead of n, you will have n to the power 1 over tau, and it will be L in power 1 over 2 tau. And then the calculation will tell you that solution will be t in power 2 tau over 4 tau minus 1, and velocity will be given by this formula, and you multiply it by m, you get m's. I changed the sign because 1 minus 2 tau will be sometimes can be positive or negative. Well, so it should be like this. And so it is a minus positive number here. Okay, so that's what's happening in a main event of main probability when these intervals are not long. And if you have single piece, that is even easier calculation. We can use exact scaling invariance of the fractal Brownian motion, which Uriel mentioned. This is the parameter alpha is the power of giving this exact relation. And it follows that PDF for velocity scales, the PDF of velocity at time t scales from PDF for velocity at time 1 in the form, this exact scaling invariance. And what it gives you that the moments, the m's moment of the velocity or speed and time t will be given by this integral, and then using exact scaling invariance, it's t to the minus alpha time m with certain prefactor, which is a constant. It's easy to see that this integral is finite. So it actually tells you also the following, that you can consider negative moments only. So m can be positive and negative, but cannot be smaller than minus 2. If it gets smaller than minus 2, then integral will not be finite. Actually, looking at this integral, the PDF at time 1 will have just PDF. It's just some function, and it just order some constant when u approaches 0. So in order this integral to be, when u is get large, it's no problem because things decay very, very fast. But near 0, you can get singularity if m is negative, and this singularity will be not summable if m is smaller than minus 2. So anyway, you should consider m only between minus 2 and infinity. And ln t will be given by this formula. And but then you have to take into account that there is a probability. This event happens with small probability, and probability is estimated here. It should be larger. Length should be larger than this scale we indicated here, that max attained within this interval. And this is probability 1 over tau in power gamma minus 2 minus 2. So that's a contribution. That is a contribution which you get here. So you have two contributions. Both are linear function of m. One is m minus m over 3, another is this contribution here. And then you want to compare and see which one is which. And now this is there's a table which shows what's happening in 3 cases. So first case is h between 1/2 and 1. That is a positively correlated thing. This is of most interest for us. And tau can be greater than 1 or less than 1 in this situation. Both is achievable because tau is gamma minus 1 to h. So if it's greater than 1, then for m large enough, depending on this number, you get one linear function. When m is between -1 and this thing, we have another linear function. And in other case, when h is between 1/2 and 1 and tau is less than 1, then the border between two things is different. And also this thing will not be -m over 3, but it will be given by this a little bit non-trivial behavior, because it corresponds to non-trivial behavior of n to the 1 over tau. Here, this last case is h between 0 and 1/2, and in this case, tau is always greater than 1. So you have -m over 3 for m larger than certain negative value, and this non-trivial behavior with another linear function between -1 and this negative value, whatever it is. So this is, in all three cases, you have bifractal behavior. You have linear piece and another one linear piece and another linear piece. It's already not one scale, but it's bifractal. It's not genuine. So that's just what we want to have true or genuine large scale multifractality. So this idea here is the following: we take H also random. So we first sample H in certain interval. And then we assume that gamma, which is an exponent of exponential decay of the interval, depend on H. And so what is described here, how you can realize this program in a particular case, which was case 1 before. So H naught will be between, so we take certain H naught between 1 and 1/2. And you take gamma naught greater than 1 plus 2 H naught, which means that you are in the case 1. And you take M naught greater than this threshold degree, so that means that you are within this formula, above formula here, not minus M/3, but this part of formula gives you the best solution. And so that's particular value of H naught, and this particular value of gamma and naught and M naught. And now you take small interval near H naught, and you want to take random H within this interval. And you also would take gamma depending on H in a particular way. And so it's easy to see that if H epsilon is small enough and H within this interval and M within this, we still will be in the case 1, because you just perturb a little bit. And conditions for case 1 are inequalities, so it will be still satisfied. And so this condition will be still satisfied. And then what will be SM? SM will be just maximum of possible SM for different H. Because you don't know, you sample different H and different H appear. And the probability distribution for H does not depend on time. It's just certain probability distribution. So all of them will contribute, and the best one would contribute most. And so you just take maximum over all H of this formula, which we got before. And now you just have to choose gamma on H in such a way that at point M naught, the maximum is attained at H naught. And then it will be non-trivially depending how the max here depend on other thing, will depend on non-trivial. So it's enough to take quadratic dependence of gamma H on H, it's a gamma naught, which we chose before, plus this factor, it's just calculation. A can be any constant times quadratic terms, and if this is your choice of gamma, then indeed at point H naught, the max will be attained, at H naught for M naught. So this, you see, this M appearing in this formula, M is a parameter, so we want to make sure that when M is equal to M naught, we get H naught, and M naught is appearing in this formula. And so so basically there's plenty of possibility to do things. So example of this is calculated here. So this is what is described before. You choose H on M by solving quadratic equation, and then find gamma M, substitute, and then it gives you SNF. That's how you find things. So for M naught, you know it will be H naught, and for other M, you just have to find H corresponding to M by solving this equation. It's quadratic equation. And then, so example will be the following. You take X naught equal to 3/4, 3/4, gamma naught is 3, M naught is 7. So for this particular case, epsilon should not be small. You can take 1/4. So you distributed it between 1/2 and 1. You take things uniformly distributed between 1/2 and 1. And then you choose gamma on H, which will be 3 plus this factor, depending on H. And this doesn't matter what you put. I put quadratic term here. I made a mistake. It should be 16. This time 16. I'm sorry. And maybe 16 is already taking effect. Maybe but it's H minus 3, 4. No, H16 is already incorporated. So this is a correct formula. And and then you do this direct calculation, and the result will be that Sm would have the following behavior. It's minus m over 3 in this interval. So you can calculate everything here. It is this non-trivial formula of m within this interval in 16. And after 16, it is minus 16 over 5. It doesn't depend. So the formula would, the function would look like it started at point as minus 1. It is a linear function with slope minus 1/3 until this value. Then it is generally nonlinear function of h until 16, and then there's a constant after 16. And that would be S on M for this particular choice of the potential. Now, we wanted to achieve, our A was to achieve multifractality in a general way, and you can achieve. Now, whether this potential we choose has some physical motivation why we choose it, I don't know. I don't think so. It is, but it carries good properties we wanted. It is stationary, has stationary increments, so that's the thing which we wanted to have it. And then you can see that power will depend on non-trivial way of the m, which considers moment of the velocity you consider. And so I think I will stop here. Thank you.
Your Kostya will be happy to answer questions. Of course, you've already asked him some during the talk.
Kostya will be happy. He will not insist.
That's
Maybe the takeaway message is that you don't put multifractality in initial condition, it's just generated by the evolution.
Yes, correct. Yes. Yeah. So evolution is created. Yes. You probably, in this particular realization, I choose H randomly at the beginning, and then I use this for all the intervals. Everywhere, but you can also choose it randomly for different intervals. And it will be no, it will be correct.
Let me just point out that the numerical part will be discussed this afternoon, so that we will get more clearer pictures and so on.
I don't know, but are you having for this potential numerics? So I think it's for
here another devilish potential.
yeah, it's another. It is a what a Bakri potential, right?
Periodic version.
For periodic Bakri potential. People are looking at how to generate quickly fractional Brownian motions, stuff like that, and then they use periodicity as an important part of generating them quickly. But it's secret of trade.
To the best of my knowledge, Bolivie was the first to come up with this fractional, what is now called.
So what people in Wikipedia mention earlier paper by Kolmogorov. Yeah, they mentioned Kolmogorov. Now I didn't look at this paper. They mentioned paper of Kolmogorov, I think in it's just Wikipedia page of fractional Brownian motion. They start with Kolmogorov, then they mention Paul Levy, then they mention then they say Mandelbrot-Ness, then Paul Levy, so all mentioned. And they mentioned first paper of Kolmogorov before. I don't know in which context Kolmogorov considered it. Yeah. But to work with this fractional Brownian motion, you basically have to use a Levy formula. That's give you control of what's going on, because real white noise have a lot of independence, so you can calculate things and you can estimate things. Otherwise, it's difficult to work. Just using correlation function, I don't know what you can achieve.
It is very important to realize that the tools for handling a non-Markov process is much more difficult than regular Brownian motion. And
That's true, but basically, it's fair to say that fractional Brownian motion, if somebody show you a picture of Brownian motion, fractional Brownian motion, like you will not be able to distinguish them. They are very similar. In any qualitative behavior needed for our purposes, you will see basically the same thing. It's wiggly. It's growing a little bit faster. It's growing a little bit faster, but
you cannot. I mean, there is a proof that with a single H you get self-similarity.
yeah, single H will not work. Yeah, single H will not work because you have exact scaling invariance. Exact scaling invariance give you just one exponent.
The first question that Uriel was concerned about was the energy decay. Because here in this calculation that you do to compute the rate of energy decay, I should take m equal 2. It
Exactly.
will give something different for the energy decay than if I take a simple fractional white noise.
Yeah. Okay.
Or will there be some difference in the rate of energy decay? I have the impression that in the end, the energy decay will be the same.
Energy decay will be the same, but well, I mean, so we have calculation of energy decay in cases 1, 2, and 3, and actually it depends on the case. In many cases, it will be like t to the minus 2/3, and in some cases, it does depend on the gamma and h. So energy, but it's single kind of single h type of thing.
There will also be some dominant terms which will lead to concepts that are decay. It will not just be 1 power of t.
But yes, you're right. I mean, it's determined. It's just your moment for m equal to 2 determines energy decay. That's correct. Yes, and then you can calculate it.
But you can change the rate of energy decay with a given h by playing with the gamma or not?
Yes, I think. Let me just. It's written in paper. And actually, before coming, I checked it.
Right,
Because I expected.
yeah, but again, we are not calculating the subdominant term.
It's difficult. Yeah, so let me just read it. Yeah.
Does it look? Okay, thanks. Okay, so Uriel already described all these things very nicely, but still for the completeness, I just recall a few things. So I'm considering Burger's equation, 1D Burger's equation, and I am writing the equation in terms of the potential. And this equation looks like equation 1 here. And this potential is related to the velocity through a differentiation. And we are considering zero kinetic viscosity going towards 0. And the randomness in the system comes from the random initial condition. And you already described it, that we have an explicit representation in terms of the initial potential for the potential at the future time t. Here we have to maximize, we have to consider this maximization throughout the whole space that we are considering. Now, in numerical simulations, we have to consider a finite one-dimensional lattice. So we will consider a finite lattice and with periodic boundary conditions, and used an algorithm which is called fast Legendre transform. This was studied by Knowles and Vargasula, and they gave an efficient method to compute this maximization, to use this formula in equation 2. Without this formula, the computation is very, very expensive, because it's like if we have a lattice of size n, then we need operations of the order n square. So that is not very useful. Using this fast Legendre transform, we need only n log n operations. So we use this in our numerical simulations. Now, out of the initial conditions that we studied, we one significant initial condition was this multifractal initial condition. Now, when we started this work, we had to tailor multifractal random walk for our numerical algorithm, and the existing multifractal random walk was not periodic. So just to recall what was known from the study of these people, Bakri et al. So they considered a sequence of random numbers of this form, which is shown in equation 3. And this sequence is constructed from two sequences. One is xi k and one is omega k. So just restricting myself for the time being to the simplest case. So xi is Gaussian white noise, and omegas are log normal variables. So sorry, e to the power omega are log normal variables. Omega is Gaussian, and these numbers are correlated with the covariance, which is given in this equation 4. And the length scale is length scale for the multifractality that this sequence shows is controlled by this parameter math cal of L. And tuning this, one can change the length scale of multifractality. Now, the important thing to implement a multifractal random walk in our numerical simulations, this sequence doesn't work, because say we start at 1, and at the end what we get, say at n, they are not close, they can be far away. So we have to find a suitable algorithm to make this sequence periodic. So what we need to do, we have to first find periodic sequences for xi and omega, and this is done by this numerical technique which was studied by Dietrich and Newsam. So in this method, you can choose a certain kind of correlation between these numbers, and then you can generate periodic sequences of this of Gaussian numbers which have a certain kind of correlation.
Question.
Yes.
The initial condition is multifractal?
Yes.
Yes.
Yeah.
Yes.
Right.
Yes.
So that was my question before to Uriel, whether the initial condition is multifractal. Say no.
So in this part of the talk, it is multifractal. In the Kostya's part of the talk, it is not.
Yes. So so using this, we can construct a periodic multifractal random walk, and we use this in our numerical simulations. So the first case is so in the as Uriel and Kostya considered. So I use multifractal random walk as initial potential. So when I do that, then I get some interesting results. So here I show in figure A the energy spectrum at different times. For example, I begin with this initial spectrum, which is shown in red. And then as time evolves, you can see the time evolution. Blue is at some smaller time, and then as time goes higher, you see that the whole spectrum becomes shows a behavior which is like k to the power -2. And if we look closely at the initial condition, we see that there are some some kind of periodicity or fluctuations. But even though we have averaged this data over hundreds of realizations, so this seems to be characteristic of multifractal random walk. And now we show in this figure B, we show how the energy evolves, energy decays in time. And we clearly see that there is some kind of, two different behavior, two different regimes. So in one regime, we have a behavior which, where the local slope is different from the late time behavior. And in this initial regime, we choose a point which is shown by these blue lines. And at this point, we see what is the behavior that's what we want to check. So just to mention, just to tell you that Hurst exponent, this multifractal initial condition corresponds to Hurst exponent h is equal to 1/2. So if we choose a smaller, large, large length scale, but not going to the, not up to the order of the system size, we'll see that this h is equal to this thing will dominate. Now, so we.
The integration is very long. I mean, it's 10 to 4. Right. So, the unit time is, the unity of time is 1. Is it?
But because
Yes, fast
logic,
logic.
you can jump to any time at once. It's not the integration of the P
Yes.
in the conventional.
Yeah. Okay, so now we focus on t is equal to 10 to the power -5, and here we check what is the behavior of the structure functions. So we computed here different orders of structure function up to order 5, and in this length scale we check what is the behavior. So here we computed the local slope, which is shown in this figure B, and we have averaged these values, and we have shown in figure C the values of this this exponent zeta p with changing this order p, and we see that it is not linear. It shows some kind of nonlinear behavior within the numerical errors. So this is quite interesting, and this shows that there is some kind of multifractality at some finite time in our numerical simulation. Okay, so this is nice. Now we can also consider multifractal data as initial velocity. And if we do so with Hurst exponent half, we again see an initial condition which has this fluctuating parts. And here also we see some kind of behavior, interesting behavior, where there are two different regimes. So in one regime, we have some non-trivial behavior, and then we have a behavior which corresponds to formation of shocks. And if we focus on a point in one of the regimes, we see that there are also some kind of signatures of multifractality left in the system. Now, okay, so now we can also consider power law initial data. So chronologically, we actually considered this power law initial data first. So this was inspired by Gurbatov et al. So in their study, Gurbatov et al, they considered initial velocity of this form. Here, E of k is some power law, and x are complex Gaussian numbers. And then they try to see what kind of decay, energy decay one gets for different exponents. So they see different behavior in two different regimes. So for -1 to when n is between -1 and 1, they see one kind of behavior. And when n is between 1 and 2, they see other kind of behavior. So inspired from this work, we considered initial conditions where the initial spectrum is constitutes two regimes, two ranges, which has two different power laws. And we can also consider initial power spectrum, which has four ranges. And this explicit form is given by this. And we try to see what kind of behavior that we get. So for two range spectrum, so here we consider initially this the energy spectrum is given by this red curve, which is hidden behind by this yellow line. Here we see that there are two ranges, and with the time, the energy spectrum behaves like this, and for different times, the energy decays, and it shows different behavior. In this different time regimes, we actually see different exponents depending on where this peak in the spectrum is. So for example, if the peak is in one power range, we see a corresponding behavior in the energy spectrum, in the local slope of the energy decay. Similarly, we can compute the integral length scale. And here also we see that there is some non-trivial behavior depending on where the peak is. Similarly, we also considered four range spectrum. So here you can see that there are four ranges, and in these four ranges, this power law is given by this vector. And when we check the energy decay, we see that there is non-self-similar behavior. And in different time regimes, we see that we compute the local slope, and this local slope is not fixed. It changes behavior according to where the peak is again. The same behavior that we saw in the two range case. And similarly, we can also compute the integral length scale. And here also we see that it doesn't grow in a self-similar way. And this is confirmed by computing the local slope. So, so in our study, we considered different types of initial conditions. So we considered two range spectrum, four range spectrum, and we observed different kind of behavior in both cases. But the multifractality that we observed in the case where we started with multifractal initial data is not observed in this 2-range and 4-range cases. So in this whole study, overall, we have considered a range of initial conditions which shows non-trivial behavior, starting from non-trivial decay of energy or growth of integral length scale, or some signatures of multifractality at some finite initial time, a finite but small time. So those things are nice, and we do not have theoretical understanding yet, but it will be very interesting to understand them analytically. If we can understand, it will be very interesting. So that's all. Thank you for listening. Yes.
You said you don't have theoretical understanding in the sense of posture.
Yes.
That's a rigorous proof.
Rigorous proof. Yes.
You have a heuristic understanding.
Yes. Heuristic is.
Right? I mean, a power law in the K space E0 of K translates into a power law decay in time. So to a first approximation, if you have two power law parts, the decay in time is basically pasting together the two powers that you would get. And eventually, at very long times, when the integral scale becomes comparable to your simulation domain, then it's just a trivial 1 over t squared. So that level of heuristic understanding we have, but we can't prove it with the lemma theorem.
Yeah, and then what time at what time the transition? I mean, is it a very long time? And is it asymptotically in time, or is it after a typical time?
You can show your plot, you go back and
You mean
It's like the blue.
blue is the local slope.
local slope?
I mean, the saturation is after a few units of time, right?
Yes.
The final saturation,
Final
which is 1 over t
Yeah.
squared, that's when the integral scale has hit the box size. But in between also there is no single power. So it is certainly not self-similar in the sense that
Can you give a rough estimate of how long these calculations have been running on the computer?
So for this particular plots, I think it is 1 day.
1 day.
1 day.
No, that's not much.
That's not much.
1 day on the
Nothing like
GPU.
On
1 day on the GPU.
Yeah. Have you been where the question that you could not answer because they would have taken many months of computations?
So the problem is the scaling with system size. So the system size we are considering is okay, but if we try to scale it 10 times, then it is an humongous time. So because FLT is still the fast Legendre transform will still take a lot of.
I will talk about the simulation of the free decay of the 3D Navier-Stokes turbulence with the same kind of initial spectrum, which Dipankar talked about a minute ago. Okay, so I start with the classical or textbook setting of the decaying problem or decaying simulation. Usually we assume the energy spectrum consists of two parts. So there's one power law part, which I wrote here as a k to the power n. And the right to this k to the power n part, we have a standard Kolmogorov k to the 5/3 spectrum. But now the energy dissipation rate is a function of time. But here we assume A and B are constant, which doesn't which do not depend on time. And the textbook result is the following. So the total energy, which is written on the bottom of this slide, the total energy decays like the time with power -2 times n+1 over n+3. And the integral scale, which is defined, again, the bottom right of this slide. So the integral scale goes like t to the 2 over n+3. So this n are coming from the low wave number part of the spectrum. Okay, so this is a textbook result that you can find in many textbooks. Okay, so yeah, let me sketch the derivation of the result. So we have two parts of the energy spectrum, and the two parts are separated by the inverse of the integral scale. So now we assume the total energy goes like t to the power alpha, and the integral scale, capital L, goes like t to the power beta. So then we demand the two parts of the spectrums are connected in a continuous manner, namely at the wave number L inverse. Those two parts are the same. So the equation 1 is the continuity of the spectrum at the integral scale, or wave number corresponding to the integral scale. And the energy dissipation rate is given by the time derivative of the total energy. So epsilon t goes like t to the alpha -1. So this is the equation 1, and we have two unknowns, alpha and beta. We need one more equations. So that one more equation is the equation 2, which is similar to the 4/5 law, but now the left-hand side is the energy, the total energy, the time derivative of the total energy goes like a minus u3 over L. The u3 is basically similar to the total energy to the power 3/2. So this equation 2 and equation 1, so we have two equations for two unknowns. So then we can just count the powers, and those simple power counting gives you the value of alpha in terms of n. N is the exponent of the low wave number part of the energy spectrum. And the beta is also given by the beta is also expressed in terms of n. So this way of estimating the power is date back to Combelot-Coursin in 1966. And yeah, this is again the textbook result. So, okay, so I showed you a numerical example of those textbook example. So I took n equals to 4. So this is a famous Lojzhansky invariance. It corresponds to the Lojzhansky invariant initial condition. So I took the initial energy spectrum, like k to the 4th times some Gaussian, and the phases of the velocity Fourier modes are said to be random, uniformly distributed between 0 and 2 pi. And Kp, K sub p is the peak wave number. Peak wave number is set to 40 here. So I used the 500 cubed. It's not a big simulation. And the kinematic viscosity is 2.0 times 10 to the -4. So on the left figure, I showed you the evolution of the energy spectrum in the log-log coordinates. So this purple line is the initial condition. And in the middle, I showed the total energy as a function of time in the log-log coordinates. Instead, you can find the logarithmic local slope. So t to the minus 10/7 is the phenomenological result I showed you. So on the rightmost figure, I plot the integral scale as a function of time in log-log coordinates, and inset you can find the logarithmic local slope of the integral scale. So those total energy and the integral scales looks like a parallel, but the exponents are somewhat different from the phenomenological theory. Okay, so now I show you the result with the hyperviscosity. So we suspect the deviation from the phenomenology is mainly coming from the low Reynolds number or viscous term. So now I have used the hyperviscosity with Laplacian squared hyperviscosity. So the initial conditions are the same, but I use this hyperviscosity, Laplacian squared. The resolution is the same as before, 500, and the peak wave number is 40, is the same. So just look at the middle figure, the total energy, and now the exponent is closer to the phenomenological prediction. And for the integral scale, again, the parallel part, the exponent is closer to the phenomenological prediction. Okay, so, and then another textbook example. So I chose the k-squared initial condition, and this is the evolution, time evolution of the energy spectrum. And for this case, I've used the hyperviscosity, and the resolution is 500, and the peak wave number is 30. So in this case, the energy and the integral scale goes like this figure. So thanks to the hyperviscosity, the parallel exponent for this case is very much close to the phenomenological prediction. Okay, so far it's just a textbook example, and the hyperviscosity gives us cleaner skating as usual. Okay, so now I like to spend a few minutes about the simulation method. So here we have solved the hyperviscous Navier-Stokes equations, and for the decaying problem, the time step in solving this Navier-Stokes equation or hyperviscous Navier-Stokes equation, delta T should not be uniform, because at the late time of decay, energy is smaller, then the delta T in principle can be larger than the initial stage. So in order to that kind of increase of the time step size can be done with a so-called adaptive time step control, which is a well-known method. And here we have used the higher order Runge-Kutta method, known as the Dorman-Prince 853 scheme. So it is eighth order accuracy, and it uses a comparison between different accuracies and to determine the error. And based on that error, we can estimate what is the optimal value for the time step. So with this method, we can increase delta T in an automatic manner. So in this figure, I showed you the delta T value of delta T as a function of time. So the purple curve is the delta T for the normal viscosity, Navier-Stokes equation. The green curve is the delta T for the hyperviscous Navier-Stokes equation. For both cases, delta T increases in time, and which is very good, because the decay time, we can perform the simulation of the decay for a very long time. But you can notice the hyperviscosity case, the time step is, the delta T is much, much smaller than the normal viscous case. So yeah, it's just a reflection of hyperviscous case. The equation becomes stiff, and the time scale involved in the hyperviscous case is much smaller than the Navier-Stokes. So this is a reflection of the nature of the equation. So for this stiff equation, we cannot get much gain with the automatic adaptive time step control. Okay. So now we move to the main part. So we consider the what we call the two-power law initial condition. So this is the same initial spectrum which Dipankar talked about. So for the low wave number part, we have power law k to the n1, and for the higher wave number part, we have different power law k to the n the power n2. So if we start with this initial condition, the phases are random as before, and we like to observe the total energy and the integral scale become non-self-similar. Namely, it decreases with several power law exponents or not. Okay, so then here, the two power law initial condition, I have chosen the exponent 1.5 and 3. It's just a random choice. It doesn't have a special meaning. I've just chosen 1.5 and 3, and the K1 is the separation wave vector between the two power laws is 10. So the scale separation is very difficult to obtain because it is a 3D simulation, and the peak wave number is 60. And here I have used hyperviscosity. So on the left figure, I showed you the evolution of the energy spectrum. So in the middle, I showed you the total energy as a function of time. So in the inset, I plot the logarithmic local slope of the total energy. So you can see there are certain plateau, which is close to some prediction value of, so this capital F is the exponent obtained with the phenomenology I showed you in the beginning. So it seems that it's probably reaches one plateau, and then maybe at a later time it may reach another plateau. But the numerical result is not clearly exhibiting such behavior. So in the right figure, I showed you the integral scale as a function of time. And again, the local slope in inset shows, it seems there are several plateaus, which probably indicates breakdown of the self-similar behavior. Okay, so now the second example is I swap the exponent of the previous example. So now the low wave number part is k to the third, and the middle, the large wave number part is 1.5. So in this case, okay, so the total energy in the middle figure decays like this figure, and the logarithmic local slope, doesn't show a multiple plateau. For the right-hand side, I showed you the integral scale. Again, the logarithmic local slope doesn't have multiple plateaus, at least for this example. Okay, so the next slide, I showed you the third example. So now the exponent is 1.5 and 2. So in this case, in one, the exponent of the initial energy spectrum is close, 1.5 and 2. So in this case, the total energy in the middle figure, decays like this figure. And if you look at the logarithmic local slope, okay, so if our interpretation is right, so the logarithmic local slope seems to have multiple plateaus, like the ones Dipankar showed for the Burgers case. For the Burgers case, there are very nice scale separations and longer time integration. and it shows clearly multiple plateaus. But in this case, the quality of multiple plateau is something like this. And for the light figure, so I showed the integral scale. So this integral scale, the logarithmic local slope doesn't develop nice plateaus. Okay, so I showed you the 3 example of the 2 polar initial condition with the hyperviscosity. So now I summarize the simulation. So we studied the 2 polar initial condition with hyperviscosity, and the question we addressed is the energy and the integral scale, whether they become so similar or not. So the simulation supports energy and the integral scale become non-self-similar because there may be because there are several plateaus in the logarithmic local slopes. And the another remark is for large T, the exponent of the total energy and the integral scale becomes identical to the phenomenological prediction of the N1. N1 is the the low wave number part of the initial, the power law in the low wave number part. Okay, so here's the end of my talk, and thank you for your attention. I stop here. Thank you.
Can you hear us now?
Yes.
Okay.
Can you hear me?
Yes.
I suppose that the Navier-Stokes 3D calculation was much, much longer than the Burgers simulations. Can you give us an idea of how long they had to reside on the best computers that you have in Japan?
Yes, but it was done in 5 years ago. And yeah, I don't remember quite well, but for this 500 calculation up to time 1000, I guess it's a matter of weeks, not months, with the shared memory machine, which is not the supercomputer, not the GPU.
Are there some calculation that you would like to do which would take months and which are indispensable to find the better fits and so on?
Oh yeah, okay. So of course, it's good to have a wider Kn1 part and a K to the N2 part. So in order to have a nice scale separation, we need to increase the resolution, like 1000, 2000. Then we have better scale separations, and then we will have a cleaner result for the non-self similarity. Or am I answering your question?
He said he's checking. All right. So first of all, thank you all for being here so late in the day. I will talk about large-scale multifractality, as for some reason I can't get this off my screen. And basically conclusions. So I will not tell you anything that you have not, oh boy. anything that you have not heard already, but I'll just bring it together. That's my goal. But first of all, again, this work was done with Uriel and Kostya and Dipankar and Takeshi, who you just heard. All the details are contained in this preprint, which is on the archive, and we hope it will be published soon. We have benefited from support from many agencies in Japan and in India and so on, but I want to highlight one especially, the French Ministry of Education, which has allowed Uriel and Ellen to bring us all together. Sort of Kostya and I have, what, 2000 probably we met first, and so we have collaborated, and my students have collaborated. And this is one of those collaborations. So I will give you an overview of this whole thing. So I will begin by recalling the motivation. Then I will give you an overview of the principal results, which I have separated into rigorous and direct numerical simulations. Then I will talk of the significance of these results, some comments, and then new vistas. So again, the Uriel covered in his talk at the beginning, the study of freely decaying turbulence is a very important problem and has a long, long history. He went as far back as Leonardo da Vinci. But in particular, the general feeling, if you read the standard texts like Takeshi mentioned, the decay of the energy E of T is always self-similar, by which we mean that it's a single power law decay in time. This is what was envisaged by Kolmogorov in 1941 in his second paper. And then it all got encapsulated under the idea of the principle of the permanence of large eddies, which was probably first formulated by Uriel, etc., in the famous Gorbatov et al. Paper and also in his book. Now, since those days, I mean, you know, he told you about Proudman and Reed, etc., there have been many studies of the decay of the energy, excuse me, for 3D Navier-Stokes turbulence. There's been experiments, numerical and approximate theory, by which I mean closure, or the sort of balancing that Takeshi just showed you. Of course, I cannot cover everything, but I recommend this recent overview article by John et al. It's John, Donzis, and Srinivasan, which has appeared in 2022. And it gives a fair overview also of the experiments, where actually, if you ask what is the decay exponent, there is a very widespread. They make a histogram of the measured exponents, and then you try to understand what that means. But as you saw in Takeshi's talk, non-self-similar decay of the energy is possible with certain initial conditions. In particular, both Dipankar and Takeshi talked about initial data in Fourier space with two power laws in the initial data, and they lead to non-self-similar decay. And then in the early to mid-90s, several groups, also, I mean, Uriel, Gorbatov, and before that, groups in Japan, Kida, etc., started studying the analogous problem for the 1D Burger's equation, which I will henceforth call Burgulence. And they first started studying initial data in real space for, let us say, the potential, which was talked about by several speakers before me. And it was found that this decay is self-similar if you have a single fractional Brownian motion with one Hurst exponent. The initial proof was heuristic, but today you saw a fully rigorous version of it. But it is non-self-similar even with one power law if the power becomes very steep in the initial spectrum as a function of k. Now, I should mention that, if you define the initial data in real space for, let us say, the potential, then if the Hurst exponent is h, the energy spectrum goes as k to the 1 minus 2h. Now, h, you will recall, was between 0 and 1, so that limits the maximum power to be k to the 1. But Gurbatov et al. First noted that you can go to k to the 1 or up to k to the 2, and if you do that, then you get certain non-monotonic behavior in the spectrum, and also in the decay of the energy with log corrections. So there, even with only one power law in the initial data, you can get non-self similar to the extent there is a log correction. All right? So that's history. That's the motivation. Now we have two sets of results, some of which are rigorous in the sense of mathematics, and some which are numerical. So let me begin with our rigorous results, which are for 1D Burgulence. So as Uriel mentioned in his talk, we have provided the first rigorous proof that the energy decays with this power law, where capital H is the Hurst exponent, with T star any reference time. And here, the rigorous proof, it's very important to establish the boundedness of E of t for all positive time. Recall that the initial datum is a fractional Brownian motion, so the energy is infinite. But suddenly at t equal to 0 plus epsilon, it becomes finite, but that requires a proof. And that's why we have a professional mathematician on our team. I mean, I can't prove it, but Kostya can prove it. Okay, and we have that proof. Then you can ask, can we generalize this fractional Brownian motion initial data in some way so that we get some large-scale multifractality? And as Kostya showed you in great detail, we have been able to define something which we call an oblivious fractional Brownian motion, OFBM sub h, with a Hurst exponent h. Then for 1D Burgulence with an OFBM h for the initial potential phi 0 of x, we can show that it exhibits intermittency and large-scale bifractality or multifractality, which is uncovered by looking at the order m moments of this velocity. The x does not matter, as Kostya said, that is translationally invariant. I can choose any x. The mth power of it, and that scales as t to the sm. Sorry?
That case is a result in time.
That's a result in time, sure. But at those large times, we are sampling very large lengths. That's why it is large-scale multifractality. X doesn't matter. X it's translationally invariant. He chose 0 actually. So it doesn't matter what X I choose. Okay? It's constructed to be translationally invariant. That's why this probability and all right, and then it is bifractal if this function S of m is piecewise linear function of m. Kostya gave you a couple of examples. And it is genuinely multifractal if it is actually not piecewise linear, but really good old-fashioned nonlinear, And he gave you an example of that. Yes, sorry, here, Lou.
It's a statement that, there is no hypothesis of multidimensionality on the initial conditions. And the multidimensionality develops.
You mean the multifractality?
Of the dynamics.
Yes, right. Okay. Yeah. And that's the clever initial condition, which is the OFBM.
Provided
you construct it properly. And in fact, what I have written here in black is proved to occur if H changes from, this is not quite correct, The way Kostya did it, it was a given H, but it had a distribution. Okay? But I couldn't summarize all that in one sentence. That's why I wrote it inaccurately. So I apologize for that. But it's written completely accurately in our preprint. All right, so those are the rigorous results. Then what can we do numerically? So again, let me begin with 1D Burgulence. So Dipankar in his talk, which just finished a while ago, showed you how you can first begin with an initial potential phi 0 of x, which is a multifractal random walk, which is a generalization of this very nice multifractal random walk of Bakri, Delors, and Musi. I think their motivational financial time series. And he had to make it periodic, as he explained to you. The important point here is that in the construction of this walk, there is a crossover length scale script L. Below that script L, it displays multifractality visibly. And far above that length scale L, it crosses over to a conventional fractional Brownian motion with Hurst H. That's in the construction of the Bakri et al. Walk. So it's a very convenient tuning parameter. So in our language, by tuning L, we can go from small scale to large scale multifractality with these initial data. Okay. Both in the initial data, and then he has checked that at finite time, the multifractality is not lost immediately. It evolves in time, but it remains multifractal by the standard measures we use to measure multifractality. Okay, so there also it is evolving in time, but it is evolving in its multifractal. Sorry.
I mean, do you
Please.
have simulations where the initial conditions are those given by the what you have in the theory, where
No, because
so
numerically we have yet another, right? Because that simulation is very hard to do. Excuse me. Right, sorry. So Pierre-Louis' question was, do we have numerics with the oblivious fractional Brownian motion initial data? Answer, not yet. Why? Because there are two levels of averaging. One thing that Dipankar emphasized was that he, first of all, even without that level of this thing, he has to average over 100 realizations. Now, to sample the probability distribution functions for the lengths that Kostya talked about, you need an additional layer of averaging. So if you did 100, then you have to do 10,000. So that's why it's not done yet, but it is on our list of things to do.
Take several weeks or months or whatever.
Well, by the time, 1 year at least, I would think. Because, you will get some things right, then you'll have to fix them and so on. Then the other type of initial data, which we have looked at, are specified in Fourier space by the initial energy spectrum E0 of K. And here we have shown you that what happens when you have a single power law, 2 power laws, 4 power laws. And this gives you a quick way of getting non-self-similar decay in time, but it doesn't seem to have large-scale multifractality by the standard measures, but we are still looking for that. All right. Then 3D Navier-Stokes. You just heard Takeshi's wonderful talk on it. I have tried to summarize it in a few sentences. First of all, by using hyperviscous DNS and this clever Dorman-Price time marching with an adaptive time step, he's been able to go to much longer times than anyone before, and therefore to look very seriously at the decay of the energy E of t and the accompanying increase in the integral length scale L of t. And to make a long story short, he just told you everything. If you have a single power law, you have a simple decay in time. And if you have two power laws, well, you have two more, etc. And I should point out one thing which was not said explicitly except in the comments, that there is a final range of crossover which happens when the integral scale grows so much that it hits the boundary of your simulation domain. Then it becomes a constant, and then trivially the energy decays as 1 over t squared. And you saw some of those 1 over t squared regimes in Dipankar's data. All right, so what's the significance of our results? You know, we've put together many different types of calculations, pure mathematics, numerics, etc. So first of all, I think we have provided the first rigorous proof of genuine multifractality for turbulence in a nonlinear hydrodynamical partial differential equation. The specific PDE we have considered is the 1D Burgers equation. Now, you might say that multifractality has been proven in the Kármán model for passive scalar advection. However, in that problem, the advection diffusion equation is linear, and the statistics of the advecting velocity field is specified. You might say, well, we've had analytical expressions for the exponent zeta p for 1D Burgulence, but these results have always yielded bifractality, never full genuine multifractality. Of course, sorry?
I mean, what's the difference? What?
Piecewise linear versus actual continuous.
No, I mean the Burgers. The research we're reporting here.
Right. So if you go back to the old Uriel, Frisch, or Gorbatov et al., if you had you know, fractional Brownian initial data for the velocity, was it, or something, then you get basically you get zeta p to be this and that, because one power law dominates, and after the shock is formed, then you just, you know, it's basically that.
And here the new ingredient.
New ingredient was oblivious fractional Brownian motion. Okay. So, of course, the mathematical proof of multifractality in 3D Navier-Stokes turbulence remains a challenging open question. That, okay.
In French, I would say, n'oubliez pas le guide, s'il vous plaît. You also understand.
N'oubliez.
Oblivious, c'est oublier. N'oubliez pas le guide, s'il vous plaît.
Okay. All right. Oops. 1 minute.
By the way.
Okay. Whoops. I thought you were the guide. Then I should emphasize the large-scale multifractality we have uncovered is non-universal, in as much as it depends on the initial condition. By contrast, the conventional small-scale multifractality that we talk about in conventional turbulence is believed to be universal. Of course, there's no proof of it, but fine, we believe that it will be. Now, some comments. There were earlier suggestions of non-self-similar decay of the energy. These were based on the EDQNM closure. For example, Aink and Thompson suggested that if you have a sufficiently steep initial condition in Fourier space, then even the Navier-Stokes evolution would show a Gorbatov type phenomenon, and non-self-similar decay could occur because of that. And in fact, now Takeshi, with his simulations, we didn't show you the data, has already found evidence of that beyond closure in a you know, state-of-the-art DNS. There were also EDQNM studies by Meldi and Sago. They had.
Can I interrupt you?
Yes.
Just a second. When you started talking about EDQNM and other semi-heuristic things, I couldn't see that could be anything
contact with intermittency and so on.
Right.
But actually, there is a
Yeah, it's coming. It's coming.
Okay. Yeah.
Right. So Meldi and Sago showed within EDQNM that if you have two or more power law initial data, you see non-self-similar decay of the energy like we found, and also a Gurbatov type phenomenon. They actually mapped it out quite reasonably. But of course, as Uriel was just pointing out, such closures cannot capture either small scale or large scale multifractality. Nevertheless, it is interesting to note that these closure schemes can get non-self-similar decay of the energy in time, just by virtue of having two different power law initial data for the energy spectrum.
So self-linear decay is not necessarily a signature of a multi.
Yes, exactly. We at first thought it was, but it's not. Now, I should also emphasize, you probably remember everything of Kostya's talk. He was always working with the Lagrangian variable A. Therefore, when we try to look for signatures of large-scale multifractality in experiments or numerical studies, we might well think of using a Lagrangian framework. And at the moment, we haven't done it very seriously in the numerics, but we plan to extend our Eulerian studies to the Lagrangian framework. And then a little bit on new vistas. I think Uriel was already mentioning that somehow you might expect that you will see something in the large scales if you have inverse cascades. So I have sort of changed the rules of the game. So far, I was talking about decaying turbulence, but now I'm sort of semi-implicitly saying I'm talking of forced turbulence with an inverse cascade. And this is an interesting idea. Of course, it goes back to Frisch, Bouquet, and Liora and Monsieur. I'm sorry?
Two-dimensional turbulence.
Yeah, 2D, but 2D, the general law is that there's no multifractality, so we thought better to do 3D. I will make another comment, which I don't have here. And it is important to examine when to think. So this would be for MHD. Now, since I mentioned MHD, I should say that there's one thing that we haven't got in the paper, but which we can prove completely, which is if you write down, and there is a well-known literature on it, and the Burger's analog of MHD, then if you work with unit Prandtl number, that is nu is equal to mu, kinematic and magnetic diffusivities is the same, then in terms of the Alzheimer variables, it separates into two independent Burgers. The moment I have two independent Burgers, I take all of Kostya's proofs and put them in there. So for Burgers MHD, we can prove large-scale multifractality. Okay, I don't know whether that's a brief report or what sort of a paper, but anyway. Now, once I gave this talk and the chair of the session was Luca Biferale, he said, oh, it's all very well to say all this, but how will you do this in experiments? So, okay, here's the challenge. So let's think of wind tunnel experiments, and we are looking at decay downstream from a grid. So the natural way would be to design such experiments. There have been earlier studies of decaying turbulence with fractal grids. But now let's try a multifractal grid. Probably not oblivious fractional Brownian yet, but we can take Dipankar's periodic Bakri et al. And you put that into the design of the grid, and then you do measurements downstream from the grid. And you can, even have a crossover length L with which you can tune. And probably you have to do Lagrangian measurements, but let's see. Last but not least, we have defined this oblivious fractional Brownian motion in the context of Burger's turbulence, but there's no reason to believe that it will not be relevant in other fields of study in physics, chemistry, biology, and finance, and we will explore this in future work. So with that, Uriel, Kostya, Dipankar, Takeshi, and I would like to thank you for your attention. Thank you.
And there is something very interesting that appeared a couple of weeks ago. It's the following. Let me rest for that. You see a big difference between Burgulence and Navier-Stokes, 3D Navier-Stokes. Is that for Burgers, we know exactly what the conditions of existence, the singularity, or etc. That's clear. Not for 3D Navier-Stokes. We don't even know if the Euler equation, the limit of vanishing viscosity, will blow up or not. We don't know. However, a very important thing is the following. As it has been proved by Russian mathematicians and then improved by other people in France and so on, if one replaces the Laplacian in the 3D Navier-Stokes equation by a power thereof, as soon as Pardon me?
Yes. I'm saying it started. It was.
I'm sorry.
Ladzinskaya first.
It's like Ladzinskaya's.
Yes, indeed. As soon as the power of the Laplacian exceeds 5/4, Ladzinskaya was 2. Yeah. Yeah. And yeah. And so then the situation is much clearer. One has all kinds of nice theorems. What do we care? We do care a lot because our results, the main one is large-scale multifractality, large scale. What I just mentioned is small scales. And there are, if you tune the thing in Navier-Stokes in 3D Navier-Stokes to 5/4 or something like that, then the situation is completely crystal clear at small scales. But the large scale multifractality is hardly going to be affected at all. Therefore, there is a possibility of really proving theorems in 3D, thanks to this that we'll explore in detail. That is something that will be added in the paper with just a few lines in the revised paper to be written in the next couple of weeks. Yeah.
Okay, that's all.
So
Yeah.
in the proof for burgers, the Hopf-Core transformation is not crucial. I mean, you can do without, or is it crucial? Because
The max formula is used.
yeah,
Yes. Hold on, let me tell you what I believe here. Actually, it's the same thing that I told you, or you remember, yesterday. Namely, in the book by Burgers of 1974, there is a very nice proof of the max formulation. And Burgers manages to, he doesn't write exactly that Hopf and Cole did it, but suggest it. But if you read the papers by Burgers and, by Hopf and Cole, you don't find that at all. My impression was that Burgers found it himself. And because he's such a modest man, he wanted to give the credit to often called, because of course it uses it, but in a crucial way that they missed.
Yeah, no, but I missed a point, because you were saying if you modify the exponent of the Laplacian in Navier-Stokes, then there is some hope to find.
Oh, that's the completely different.
Yeah.
We are talking about Burgers.
Means the problem is well posed, so we can do mathematics.
Right.
Yeah, but it doesn't mean that,
No, no.
that it's easy to find the proof.
I mean,
to my opinion, Hopf-Kohl was crucial in Burgers, and so transforming
No, no.
Navier-Stokes into
The two remarks are unrelated. They are unrelated.
Yeah.
What I said about small scales before has nothing to do about who derived the Max formula for Burgers equation.
Yeah.
At least I would say Hopf, Kohl, and Burgers.
Well, let me comment on this. So you can derive Max formula from Hopf-Kohl, but actually it's much more general result. The variational principle holds for variety of equations of non-linear type, say quasi-linear equations. And that's called Lax-Salenic variational principle. So the variational principle holds even if there is no Hopf-Kohl. Hopf-Kohl is just way to derive it for particular equation and the limit. It's more general statement.
Yes.
And actually,
That's what the core equation.
and actually it was developed by Lax-Salenic in middle of 50s.
50s, yes.
Yeah, so it's
Just after Hopf and Kohl.
it's a little bit after Hopf and Kohl. I don't know whether they were kind of inspired or not. This I don't know, but definitely much before the book of Burgers in 70s.
I think that's a good point. Yes.
So probably Burgers didn't know this Max formula initially, and then he got this understanding after the Hopf-Kohl transformation. But whether he knew, I mean, we should look at the book of Burgers whether he's citing Lax-Salenic.
Yes, indeed.
Mr. Font, you're saying that the Max formula is not necessarily a consequence of a Hopf-Kohl.
Yeah, you can get it.
You can
without
derive
reduction
it.
to
You can
indication.
derive it independently. from-
Absolutely. And
So
it
you
and
could,
it
for
is
example,
true for equations which are not reduced to linear equations.
so you could work it out not
We
for
should
Burgers,
write
like
a paper.
Kuramoto-Shirachinsky, for example.
Yes.
For
Kuramoto-Shirachinsky.
this, I don't know.
Well, probably not because, well, we have to check, but not because there is viscous dissipation in Kuramoto-Shirachinsky, right? I mean, there is a scale dependent, right? Right. So it is unstable for some modes and stable for others, and then the nonlinear. Right, right. So, you know, I don't know. I'll have to show it to Kostya before I can answer your question.
So I mean, if you replace phi x squared by phi x to the 4 in the equation, then there is no Hopf-Kohl.
Yeah.
But the variational principle holds.
Okay, and then you can prove it.
Yeah, that's a good
Yeah,
point.
the same thing.
So can you prove it for multi-dimensional Burgers equation, for example?
Probably yes. Whenever there is a variational principle, we can. Now the connection with fluid mechanics is less clear. Because this is equation for potential phi. Then gradient of phi is not a velocity, it is momentum. And then you have to define velocity through Legendre transform. So there is a whole machinery. So the equation is not directly related to. So for Burgers, this momentum and velocity coincide. It's like a quadratic Hamiltonian. Generally, they're not.
There is something that I perhaps should mention. The Rahul insisted very much that in our paper we should give some experimental perspective, correct?
Yes, yes.
However, that is true, But that was also the case of Kolmogorov. Kolmogorov even would spend time on boats and to see what is happening there, and got a real feeling for hydrodynamics as it works. Mm? So it's a very important thing to. I mean, we don't have an experimentalist among us, but perhaps we should add one.
Well, we will have,
You
yes.
have to have confidence in the boat.
Mhm.
Yeah.
That's very popular in Russia.
Right.
The advantage is that there's no escape. People cannot go anywhere. They will be there anyway.
Okay. Any other questions, comments?
Just the time.
Yes, 240, Kostya has a finite time singularity at 3. So,
Oh no, it was supposed to end at 3. Yeah, but or before.
Yeah.
Yeah. Yeah. Because
Thank you.
you're
Thank you very much.
thank you. Thank you. All right, I guess they will do this.
Thank you.
Yes, I know. I was going to say that. Ellen, thank you very much for doing this great thing.
Great catering.